Hello and welcome to our brief video explaining atomic instructions and how they relate to operating systems. What are atomic instructions? Atomic instructions are hardware instructions that perform an operation on one or multiple memory locations atomically. This is a lot of fancy words to say that we do some group of actions as one unit or as one uninterruptible action, even if it is more than one action. Why? In operating systems, multiple processes sometimes need to use and make changes to the same piece of data. This can be very dangerous and it is what is called the race condition. Let's explain why. The following examples are multi-instruction methods used as one uninterruptible one. They help us avoid that pesky race condition we just talked about.
To explain atomic instructions, we first have to explain the problem that they solve. And one of the major problems that they solve is the race condition. The race condition is the idea that two processes working on a shared variable compete with each other and overwrite the processes of each other because they can't tell when something that they have read has been changed. And the underlying concept is that any regular instructions, any regular functions that are done to this variable are not done as one uninterruptible process, as one atomic process. They are done as multiple individual instructions. So let's use the example of the increments. We've got two processes here, both of which want to increment this zero variable. You would think that when both processes increment the zero variable by one number, that's in the end of both of them running, 0 would now be 2. What actually happens if they're running simultaneously is an example of the race condition. And the reason for that is simple. Increment process 1 needs to, in order to increment 0, read the variable from the memory location, modify that variable, and then write that variable back to the memory location. That is how the increment process works. Increment process 2 does the same thing. It reads 0, it modifies 0, it writes it back. So let's see how that works in practice. Process 1 reads in 0, so it says 0. Process 2 also looks at the memory location. It sees a 0 there. Process 1 modifies that 0, changes it to a 1, writes that 1 back to here. The 0 in the memory location is now 1. Process 2, without recognizing that process 1 has already changed it since the last time it has read it, increments 0 to 1, overwrites what was in the memory location, makes it 1. Instead of being incremented twice, we've just incremented it once and then overwritten the original increments with another value of 1. The way that we solve that is with atomic instructions. If these increment processes are atomic, then the read, write, modify are done as one set without being interrupted by anyone else. Anytime that process 1 is trying to increment 0, process 2 cannot access the contents of 0 until process 1 is finished accessing them. So the increment process becomes increment process 1, read 0, modify 0, changes it to 1. Even if process 2 wants to read 0 at the same time, it cannot because process 1 is using an atomic or uninterruptible instruction. So it now changes it to 1. Process 2 waits for the changes to be done by 1, then goes in and does its own atomic increment process. It sees the value of 1, it modifies the value of 1, it increments it by 1, and now in the memory location we have the number 2.
So to really illustrate what the atomic instructions really is, we wanted to use a game scenario of tic-tac-toe. What happens is that when the player 1 gets the table, puts the X here, let's say, and then updates it. Then player O, or at the same time, gets the table, and then places an O. Let's say player decides to place it here as well. Since it's seen it empty in this position, maybe he decided to put it there. Now what happened is that player X played here, player O played exact same location. Since they're not synchronizing the information, they are really not playing on the same board. When they make changes, they should have updated the very table in between, so then they're playing in the same game. They're synchronizing. Let's talk about what happens if they synchronize. Okay. Now, this setup is the same. Now, what changes is that during the time that process 1 is adding its value, so it's going there, picking it up, bringing it back, and then putting this X. During this time, player O cannot change the table. Only player X has access to it. And only once, when the process 1 is done, in which scenario it would update this table with X. Okay? And then this is the updated version. Player O would then get the table, which would look like this, with an X here. Then player O would add its O wherever he wants to. Let's say he wants to put it here. Fine. Then player O would update it to be like this. And during the time player O is putting that O, player X cannot update the table. So while process 2 is working, process 1 can't make a change on it. Process 1 is working, process 2 can't make a change on it. So in the broader aspect, atomic instructions are aimed at synchronizing processes.
Test and set. Test and set is used as a locking mechanism, creating a single variable, generally the number 1 or 0, where 1 is used to symbolize locked and 0 is used to symbolize unlocked. If when we check the lock it is set to 0, we switch the lock variable to 1, do our work, and then switch back to 0 after. If it is 1 already, we wait for it to become 0. Fetch and modify. Fetch and modify solves our incrementation problem. Instead of modifying in 3 steps, read, change, write back, we use the fetch and modify instruction. The operating system and all the processes see this as one instruction and no race condition occurs. Compare and swap. Compare and swap compares the value of a memory location with a given value and only makes changes to the memory location if the value of the memory location is the same as the given value. Otherwise, we do not make a change.